The Boeing 707 that opened the jet age in 1958 cruised at 525 knots. The Boeing 787 replacing it today typically cruises at 488 knots, slower, not faster. Across the whole modern fleet, from the 737 to the A350, cruise speeds have quietly dropped since the 1970s, even as the planes themselves got bigger, longer range, and more advanced. But this isn't engineering going backward. So why did the industry choose to slow down? And why does it keep choosing that, flight after flight? The answer involves a 400% oil shock, a quiet onboard setting most passengers have never heard of, and a supersonic jet the world's regulators effectively banned from reaching the customers it was built for. In October 1973, global political shifts abruptly rewrote the fundamental math of flight. The OAPEC oil embargo ended the era of cheap aviation fuel almost overnight. Crude prices rose from $3.60 a barrel to over $9 a barrel, causing jet fuel costs to quadruple. Before this shock, fuel was a minor line item, often accounting for less than 10% of an airline's operating expenses. Suddenly, it became their largest single cost. This immediate spike transformed speed from a competitive advantage into a direct financial penalty. Flying faster requires overcoming aerodynamic drag, which increases exponentially with velocity. When fuel was inexpensive, airlines willingly burned extra tons to shave minutes off flight schedules. In the post-embargo market, those minutes became luxury items that carriers could no longer justify. Slower, more efficient operations became an economic necessity. To address this new reality, NASA launched the Aircraft Energy Efficiency Program in 1973, a major research initiative that ran through 1987. Directed by Dr. James Kramer, the project aimed to reduce commercial fuel consumption by up to 50%. Instead of designing engines to push planes through the air at higher Mach numbers, researchers focused on maximizing aerodynamic efficiency. This federal effort accelerated the development of supercritical wings and high-bypass turbofan engines, technologies that perform best at slightly lower cruise speeds. The industry did not abandon its ambition. It redirected its engineering toward a new, harder objective. Speed was traded for survival. The early turbojets powering the Boeing 707 and Douglas DC-8 were designed to push through the air at high velocities, routinely cruising between Mach 0.82 and 0.84. These low-bypass engines generated thrust by accelerating a relatively small amount of air to high exhaust speeds. While effective for raw velocity, this method consumed immense amounts of fuel. The subsequent development of high-bypass turbofans altered the engineering equation. These modern power plants feature a large front fan that bypasses a massive volume of air around the engine core. While this design significantly reduces specific fuel consumption by capturing more propulsive efficiency, the physics of large-diameter fans limits their peak performance to lower cruise speeds. As high-bypass engines became the industry standard, aircraft manufacturers adjusted their designs to match this new thermodynamic sweet spot. Consequently, while the older 707 and DC-8 generation operated at higher Mach numbers, modern narrowbodies like the Boeing 737 and Airbus A320 families are optimized to cruise below Mach 0.78. This speed reduction represents a deliberate engineering trade-off. Manufacturers did not lose the ability to build faster passenger jets. They chose to optimize airframes and engines for the lowest possible fuel burn per mile. If this were only about which engine got bolted on, it would be a simple footnote, but it is only the first reason. How does an airline translate these physical engine limits into a daily flight schedule? The answer lies in the fact that carriers do not fly jets at a single, predetermined cruising speed. Instead, the velocity of a modern commercial flight is governed by a dynamic mathematical calculation programmed before every takeoff. At the center of this calculation is the cost index, a dimensionless ratio entered directly into the flight management computer. The mathematical formula is exact: the cost of time per operating hour, which includes crew wages, hourly maintenance contracts, and gate delay penalties, divided by the cost of fuel per kilogram. Depending on the aircraft manufacturer and model, These programmable values can range from 0 to as high as 500. By altering this single input, airlines dictate how the automation balances the trade-off between time and fuel. A low-cost index, often between 5 and 15, indicates that fuel is expensive relative to time. The flight management system responds by calculating a slower, highly efficient cruise speed to minimize fuel burn. Conversely, when a flight is delayed and risks missing tight arrival windows, the crew inputs a high-cost index. This command tells the computer that time-related penalties outweigh the expense of fuel, prompting the system to select a faster cruise speed to shave minutes off the trip. The onboard computer continuously parses this ratio against real-time wind and weight data to determine the optimal speed for every specific mile of the route. Speed is no longer a fixed design performance metric. It is a live, automated financial calculation. To see this mathematical lever in action, consider how a single airframe operates on different days. On a routine flight, a carrier prioritizing low fuel burn might input a low-cost index between 5 and 15. For an Airbus A320, this command programs a fuel optimal cruise speed of Mach 0.76. But if that same aircraft falls behind schedule on its next leg, risking missed passenger connections and expensive gate penalties, the dispatcher can raise that value to 50 or 80. This adjustment signals the flight computer that time has become more expensive than fuel. The system immediately recalculates the flight profile, raising the cruise speed to Mach 0.79. While a shift of Mach 0.03 sounds minor, across a 5-hour flight, it trims roughly 10 to 15 minutes from the block time. But speed is never free. Shaving those 15 minutes off the arrival time requires the engines to burn several hundred kilograms of additional fuel. On a typical mid-range sector, a carrier might burn an extra 500 kilograms of Jet A just to gain those few minutes. If fuel prices are high, that minor speed boost can add thousands of dollars to the flight's direct operating costs. Airlines run these trade-offs constantly. Low-cost carriers consistently lock their flight computers to single-digit indexes to protect their narrow margins. Legacy network carriers managing complex hubs with thousands of connecting passengers lean toward higher settings to protect their schedules. The very same physical aircraft will fly at entirely different speeds on the exact same route, hour by hour, depending on the price of oil and the pressure of the clock. The aircraft is not flying at its maximum physical capability, nor is it locked into a single design speed. It cruises precisely as fast as the math says is worth paying for. If the speed limit of modern aviation were solely a matter of engine bypass ratios and cost index calculations, the story would end with subsonic optimization. But there is a third non-aerodynamic barrier to speed, one that has nothing to do with the physical engines bolted to a standard passenger jet. What happens when an aircraft successfully bypasses these subsonic trade-offs altogether? In 1976, the commercial aviation world seemed to find its answer when Concorde entered regular service. Cruising at Mach 2.04, this technological marvel traveled at more than double the speed of sound, crossing the Atlantic in under 4 hours. It was a flawless engineering triumph over the drag divergence barrier. Yet Concorde immediately collided with a different kind of limit. In 1973, 3 years before Concorde's first commercial passenger flight, the United States Federal Aviation Administration enacted a strict ban on civil supersonic flight over land. Codified under Title 14 of the Code of Federal Regulations, Part 91.817, this policy outlawed supersonic speeds over the American mainland due to the disruptive noise of the sonic boom. This single regulatory decision confined viable supersonic operations almost exclusively to ocean-crossing routes, primarily the transatlantic corridor between Europe and the East Coast. A technically successful speed solution had run headfirst into a policy wall. Even with route restrictions, Concorde faced an internal financial limit built into its own fuel tanks. Traveling at Mach 2.04 required turbojet engines that incurred a severe efficiency penalty. Concorde burned roughly 4 times more fuel per passenger than a comparable subsonic jet on the exact same route. Operating such a flight was the economic equivalent of driving a school bus alone to work every day. How did these physical realities translate into direct airline operations? A single transatlantic crossing consumed approximately 17,000 gallons of fuel to transport only 100 passengers. The exact mathematics of this fuel penalty became clear when measuring transport efficiency. Concorde delivered a mere 17 passenger miles per gallon. In contrast, modern subsonic airliners achieve between 50 and 80 passenger miles per gallon. To offset these high operational costs, operators had to charge extraordinary ticket prices to guarantee even a chance of profitability. A round-trip ticket between London and New York routinely cost between $8,000 and $12,000. These extreme fare levels turned supersonic flight into a financial outlier, completely isolating it from the mass passenger market. The aircraft did not operate as a scalable transport system. Instead, it served as an ultra-exclusive shuttle for a tiny segment of corporate executives and affluent travelers who could afford to prioritize time over a realistic budget. This extreme cost structure meant that speed remained a niche product, unable to compete with the cheaper, slower models dominating the global skies. While subsonic carriers filled thousands of seats daily at lower prices, Concorde flew mostly empty cabins on all but its most popular routes. Slower flight remained the only path to a viable mass market. The fragile economic model of commercial supersonic flight was ultimately shattered by a single tragic afternoon. On July 25, 2000, Air France Flight 4590 crashed shortly after takeoff from Paris, resulting in 113 fatalities. The disaster forced an immediate grounding of the Concorde fleet for expensive structural retrofits, which severely damaged public confidence in the safety of high-speed travel. When the modified aircraft eventually returned to service in late 2001, they entered an entirely different market. The post-September 11 downturn in global aviation caused a massive collapse in premium travel. Corporate budgets tightened, luxury travel declined sharply, and the wealthy passenger base that Concorde relied on vanished. Faced with escalating maintenance costs and empty cabins, the business case for supersonic flight was gone. British Airways and Air France officially retired the fleet in 2003, bringing the first chapter of commercial supersonic flight to a permanent close. Documentaries like this are made possible through the support of our viewers. For those interested in the engineering decisions that shape modern transport, our library offers several detailed studies of industrial design. A common perception suggests that aviation has stagnated, yet the downward shift in speed represents a deliberate victory of efficiency. The fundamental question is never whether engineers can build a faster aircraft, but whether saving minutes is worth the added cost. Every minute trimmed from a schedule must be weighed against exponential fuel burn, structural demands, and regulatory barriers. This arithmetic governs the industry at every level, from supercritical wing designs and cost index settings to the abandonment of supersonic networks. Slower won because the mass market would not pay for speed. The modern airliner could easily go faster, but the extra speed is simply not worth the fuel. Today's flight path is a carefully calculated compromise among engine efficiency, cost index mathematics, and a supersonic dream that regulators and economics ultimately rejected. Subscribe to the channel for more engineering analyses. The industry responded to the speed limit by changing the geography of flight itself. Instead of pushing aircraft to fly faster between major hubs, manufacturers built long-range, mid-sized wide-bodies like the Boeing 787 and Airbus A350. These aircraft bypass hubs entirely, linking secondary cities with non-stop flights. Eliminating a single 2-hour connection reduces total travel time far more than a slight increase in cruise velocity ever could. To squeeze more efficiency out of these subsonic airframes, engineers turn to aerodynamic refinements rather than raw power. The addition of upturned wingtips, or winglets, alters the airflow at the wing ends, reducing lift-induced drag. This modification provides a 3 to 5% fuel savings at standard cruise speeds, allowing airlines to lower operating costs without entering an expensive speed race. Ultimately, the design of the modern aviation network reflects passenger behavior. Market data consistently reveals that the vast majority of travelers select flights based on ticket price rather than a marginal reduction in travel time. Airlines responded by structuring their fleets for high seating capacity and fuel efficiency, transforming flight from an exclusive high-speed luxury into an affordable utility for mass transit. Boom Supersonic is currently developing Overture, a passenger jet targeting a cruise speed of Mach 1.7, with a planned entry into service by 2029. To bypass the high fuel burn that doomed Concorde, the design relies on an efficiency-first engine architecture designed to run on sustainable aviation fuel, a fuel that could alter the operating cost equation. Yet the physical and regulatory barriers remain largely unchanged. Under Title 14 of the Code of Federal Regulations, Part 91.817, civil supersonic flight over the United States mainland remains restricted. While the FAA is evaluating a performance-based limit of 75 EPNDB, supported by data from NASA's X-59 Quest flight tests, any supersonic return remains constrained by these noise boundaries. Overture must not only fly faster, but it must also survive the same unforgiving economic arithmetic that has governed the commercial market for 50 years. Speed is only viable if the economics balance. Airliners today could fly faster, but physics cannot outrun economics. Slower cruise speeds reflect a calculated compromise of engine efficiency, cost index mathematics, and a supersonic ambition that regulators and balance sheets ultimately rejected. In modern aviation, progress is measured in fuel saved, not minutes gained. Subscribe for more analytical engineering insights.